Oh, I'm going to the
Why does it theology? You have to.
No, tomorrow.
Well, you have to take advantage.
So, last
I'd
time,
rather just do it.
we started counting a bunch of stuff. And we had several situations that we wanted to pay attention to. We had the multiplication rule. Right. And so that was if A, B finite sets, then the number of A, B would be equal to the size of A times the size of B. That's the number of tuples you can make where the first guy comes from A and the second guy comes from B. So that was the multiplication rule. You can also think of this as an experiment in several stages. The size of A, if I call that n, there are n ways for this to happen, n ways for that to happen. To put these all together in one thing, it'll be n times n ways. We also had if we have A is a set with size n, let's say it has n elements, then the number of m tuples, right? That means that coordinates that look like they have m things in it, and m is less than or equal to n. That was equal to n raised to the n power. We also saw, similarly, A is a set with size n. Then the number of m tuples with no repeats. This was equal to n times n minus 1 all the way down to n minus n plus 1, and this we gave it a name. We call this P n m. The number of ways to take m objects out of n objects and arrange them in a certain order. We also derived a formula for this, and it was n factorial over n minus n factorial. We also saw that there was a special case here. P of n comma n, where you're putting n things in order, and we saw that that was n factorial. This was the number of ways to arrange n objects in some order. Or you can even think of it as the so one way we want to think of this one is the number of ways to choose m objects from n objects and put them in order. So this guy came from us counting tuples, so the order actually matters the rearrangement. So every time you're dealing with one of these guys over here, the order actually matters. That's going to be important. But order matters, but there's no repeats. Here, order matters, you allow repeats. And this is multiplication. Actually, order doesn't really matter here, but for this one, the order actually matters. Now, let us continue this idea. I want to actually talk about another situation that we can have. It's where we are given a set and we want to create sets from that set, not tuples. Meaning, I want to create subsets of that set, so there's no inherent order in how I'm choosing things. So that's the next thing I want us to figure out. Let's figure out if A is a set with the size, there are n things in the set, how many m sets can be created? Where n is less than or equal to n. So I have a set with so many things in it. I want to pick out a certain number of those things and create sets from those things. Let's actually figure that out. Let's look at an example. What am I talking about here? Suppose A is the set A, B, C, D. How many two sets can be formed? Is what I'm asking. How many different ways can I create subsets of size 2 from this set of size 4? So if I'm choosing from a group of 4 things, I want to pick 2 things at random and put them in a set. How many ways can I actually do that? Here, let's just enumerate. Right, so that's the basic way of counting. And you can sort of do it in a certain order. So one thing you can do is you can have A in the set, and then you can choose the B. Another thing you can do is you can have A, then you can choose the C. You can have A, then you can choose the D. Right? So these are all the 2 sets that I can create that have A in them. I can continue this process. Let's say I have a set with B in it, and I can pick someone else. Now, I can't pick A in this scenario, because if I pick A, it's equal to this set. Remember, sets don't care about order. So I can't put the B and the A together again. But what I could do is pick the C. Or I could have the B and I pick the D. And that's all the ones I could pick. I cannot pick the A because that will just copy this set. So then I can say, okay, what about the set with C in it? What could I pick? Well, I can't pick A because that set already exists. I can't pick B because that set already exists. I can pick D. And that's all the sets that I can create with the C. Now, is there any set that I can create with D in it that hasn't been created before? No. Well, if I pick the A, I get this guy. If I pick the B, I get this guy. If I pick the C, I get that guy. So no, there are no more sets. This is all of them. So it turns out the answer to this is 6. There are 6 possible ways to take out 2 sets from a set of size 4. Now, that's with enumerating. You probably don't want to do that all the time. We're going to want to figure out a general way to do this. So let's actually illustrate that with a slightly larger A, B, C, D, E, F. How many 4 sets can we make? So I have a set of 6 things. How many ways can I actually take 4 things from this 6 things in a way that order doesn't matter and I'm not allowed to take a repeat? Now, I'm not going to enumerate. I'm going to kind of illustrate to you the thought process that is going to go into the formula that I'm about to give you. And here it is. Let's say, focus on one possible set. Say I could create a set with A, C, E, and F. Right? That's one possible set that I can use. Now, we don't yet know how to count sets, but we do know how to count tuples. Right? Now, how many tuples would correspond to this set? Well, if I have the A, C, E, F, well, one possibility is that I just throw this in a tuple in the order it was written, but I could also create another tuple where I can switch the E and the C. I can create another tuple where I can switch the F, the A, the E, the C. I can create another, right? I can do this a bunch of times. Now, here's the question. How many times would I be able to do that? Now, this puts us in a situation that we were in last class, actually, right? I have a set with 4 things in it. How many tuples of size 4 can I make? Well, what's the answer? So, non-repeating?
4 factorial.
4 factorial. There are 4 factorial of these guys. There are P of 4 equals 4 factorial such things, such tuples. However, if I was counting tuples, I'd have 4 factorial. That's 24 permutations. However, with a set, all of that collapses into one thing. So in other words, what are we saying? So from this, here's what I can say. The number of sets of size 4. Okay? I want to actually compare that to the number of tuples of size 4. So now, for every one of these, how many of those do I have? Well, in this scenario, I'm going to have 4 factorial of those. So it turns out if I take the number of sets of size 4 that I can create, multiply by 4 factorial, that means I can rewrite the items in any order, but the set doesn't actually care. I can get the total number of tuples. In other words, the number of 4 sets is going to be equal to the number of 4 tuples divided by 4 factorial. And how many 4 tuples could I actually create? Well, going back to the original, there were 6 things. The number of 4 tuples I can create from 6 things would be P of 6, 4 over 4 factorial. So that's just illustrating how we can actually figure that out for this particular example. By the way, this would actually be 6 factorial divided by 6 minus 4 factorial all over 4 factorial. Or in other words, 6 factorial over 4 factorial times 6 minus 4 factorial. Let's write this down in general. And these are numbers. We can actually compute that number. That's how many 4 sets I can create from a set of size 6. So, now in general, this means if A is a set with the size of A is n, the number of m sets of size m that can be created is n factorial over n m factorial times n minus n factorial. Just by me using, replacing the n with the 6 and replacing the m with the 4 in the previous example, I get this number. And it's not just some random number, it's a very important number. In fact, it's important enough for us to give it a name. We call this number a combination. And we denote it by C and M. Or you might see C and M, or you might see this notation and put M down at the bottom. Right? No division sign. It's just like one long parenthesis, put one number in the top, one number at the bottom, and that's called a combination, i.e. C of n m is equal to n factorial over m factorial times n minus n factorial. This is now an important formula. At this point though, you don't even have to really know the formula, because if you have a calculator like the TI-30 or whatever was recommended here, you should be able to find these numbers on your calculator. So take a moment right now, make sure you know how to find these numbers on your calculator. Make sure that you know how to find P and M and C and M. Common variations to this is R instead of M, so P and R would be the same thing, or C and R. Or you can see C and R, or you can see C and R. It's going to look something like that.
On some is it like N and then CR?
Yes, on some calculators it would look like N, C, R as well. There are many notations, so look in your calculator for one of those guys. Probably the most common ones would be like this or that. NCR or NPR.
Yeah, you can like 6. It's the one that was on my tier before.
Mine just is
What is every yellow?
And when you find it, let's actually check that you know how to use it. Compute the following with that calculator.
Are we allowed to start using TI-84s now that that's the matrix part?
No, we're going to be doing matrix stuff later. So compute on the calculator. Let's do C. 25 choose 7, and P 34 choose 9. Tell me what answers you get here.
How do you enter it?
So with a lot of calculators, you enter the first number, you press whatever symbol is for that button, then you enter the second number, and then you press Control.
Oh.
So I'm sure you know how that is.
Oh, I got it. Wait, what did you get?
Okay, what do you guys get?
I got 480,700.
Yeah, that's what I have. Did everyone get that? You should be getting that. Or else this one. This one's big. Yeah.
Oh,
That's a big one.
alright, word. Oh, yeah.
By the way, that's how many ways you can, in a set of 34 things, for you to pick 9 random things, put them in a very specific order, you can do it this many ways. Out of a set of 25 things, if you were to pick 7 random things, not caring about what order in which you pick them, you can do that 480 80,700 ways. Now you don't want to have to count that, like enumerate. That's something that you should want to figure out. Now, to something else that you should know, NCR is often called N-choose R. Right? So, in other words, it's the number of ways to choose R objects from N objects. Order does not matter. And of course, no repeats, because what we're doing is we're choosing new sets out of old sets. So, if you ever have to count anything in that situation, you have a group of things, and you need to pick some subgroup of things where you don't care about the order in which they're picked. This is going to be the number of ways you can actually do that. And you should now know how to actually find that on your calculator. And the formula I wrote down here is the version that's in your textbook. But yeah, so once we figured out how to count tuples, we automatically know how to count sets now, just by dividing out all the extra stuff that we get from tuples. We divide out the permutations. So we can have this guy, which is called a combination. Right? Just ways you can combine things without worrying about order. And this guy is called the permutation. It's the way that deals with the different kinds of arrangements that you can have. And of course, as you would probably guess, this guy is always going to be bigger than that guy. Because this guy is counting sets, and for each set, you can have rearranged the elements in multiple ways. So this is going to be bigger than that all the time. Common mistake is, I guess I'll talk about common mistakes of mixing these up when we get to actually probability. Now let's stick to actually counting. And what we're going to do is start to flex our counting muscles with these problems. And next time I'll again summarize all the new numbers that we know, all the new ways that we know how to count, because it can get confusing when you're not used to it. But for now, let's actually just jump in there, get our hands dirty with some examples. So let's do, and I posted an electronic version of this counting examples on the website. Problem 1. Let's suppose you have 3 shirts and 2 pants. Nothing else. That's all you have. That's all you have to your name. 3 shirts and 2 pants. How many possible outfits could you create? Yeah?
3 pick
Huh?
3 pick one and 2 pick one.
9.
Okay, so let's think about it this way. What methodology would you use? That's the first thing you want to do. Yeah.
Can you treat these 2 different sets as multiplication?
Multiplication was what I would think. Why? You can think of getting dressed in stages. We have 2 stages. There's stage 1. Pick a shirt. How many choices do you have? Well, you have 3 choices. The second stage, stage 2, is to pick a pants. How many choices do you have there? You have 2 choices. So it's like your A is the set of shirts, your B is the set of pants. You want to create a coordinate with 2 of these guys in it. There are 3 choices for the first coordinate, there are 2 choices for the second coordinate. The multiplication rule tells us that 3 times 2 equals 6 is the total number of choices. There are 6 total possible outputs that you can create. So this is how we're going to use those numbers. So when I'm describing in words what these numbers are describing, that's what you're going to use to figure out how you're going to count something. So you're going to read some situation and you're going to think, what is the best way for me to think about this? Is it the multiplication rule? Can I think of it as in tuples? Does order matter? Does order not matter? Can repeats happen? Can repeats not happen? You would use different things based on the situation. So problem 1 is a straight up multiplication rule. Problem 2. You toss a fair coin 3 times. How many possible outcomes are there? How do you visualize this one?
Sets.
Sets.
We just list out, we just do choices.
Okay.
We just list them out. It could be heads, heads, tails, tails, tails.
That's 3 times.
From the end?
I misunderstood.
Right, so I mean, if we put it in sets, it's going to be a problem if I get heads twice. It's going to get erased, right? Because the set doesn't care about repeats. So one thing you can do here is you can think count tuples, where we're counting 3 things. What's going on in the first toss? What's going on in the second toss? What's going on in the third toss? And how many choices would I have here?
2.
2. 2. And 2. So there are 2 to the cube, or 8 possibilities. You could also think of the multiplication rule here. Think of each toss as a stage. Stage 1 is toss 1. Stage 2 is toss 2. Stage 3 is toss 3. Could also think multiplication rule here. Right? Think of each toss as a stage. You wouldn't think sets because if you get the same thing twice, the set is going to forget that you got the same thing twice. It will erase the repeats. You toss 2 fair 6-sided dice. So hopefully you know what a dice is. It's a thing. It's cute where there are numbers on this thing. There's numbered 1 through 6. You have 2 of those things. If you toss a dice, how many possibilities are there? Why 6?
Because there's 6 times.
6 per die.
6 per die. What does that mean? Yeah?
Each one is 6 down, so it's 6 squared.
It's 6 squared. Again, think stages. First die. And the second die. 6 choices here. 6 choices there. There are 36 total choices. When it comes to dice in particular, there's a nice little thing that we set up sometimes that it's going to come in handy later on. You can put it in a table. So there's die 1, die 2. It can be 1, 2, 3, 4, 5, or 6. This one can be 1, 2, 3, 4, 5, or 6. Now, of course, here you'd have like the first die is 1, the second die is 1, the first die is 1, the second die is 2, the first die is 1, second die is 3, first die is 1, second die is 4, and so on. Sometimes we're going to want to be able to count things like what do the faces add up to? And I would put a 2 here, 3 here, 4 here, 5 here, 6 here, etc. Or what is the difference between the two faces? And then I put 0 here, 1 here, 2 there, etc. Right? So depending on what you're counting, you can actually lay it out in a table where you have 6 choices going either way. And this is just a visual representation of the multiplication rule, right? Because it's going to be 6 by 6. Which is going to give you 36 total possibilities. 36 total choices when you throw 2-sided dice. So be aware of what we're doing here. Everything we're counting is interpreted in terms of the things that we learned between last class and this class. So don't just randomly try to think of, oh, I wonder how many that's going to be. No. Is it a tuple? Is it a set? Does order matter? Does it not matter? Think of it as an experiment with several stages. You have to have a method for how you're thinking about the problem. You could do this and list everything, but why spend the time? It's 6 times 6. How many possible 10-digit phone numbers are there if the first digit must be 1? What are you thinking? Yeah?
Can you mention the options? First spot is a 1.
Yeah, so in the first spot there's a 1.
And then for every
And 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah.
So isn't it 10?
10 to the 9, because you have 10 digits that you can put here, 0 through 9. You'd have 10 digits you can put here, 10 digits you can put here. We were given no other restriction other than the first must be 1. So this is for it's the first stage is the first digit, second stage is the second digit, and so on. So this is equal to by the multiplication rule. 10 to the 9 total choices. It's a billion possible phone numbers. You would not want to enumerate that. Discussing my class yesterday. You know how long it will take you to count to a billion?
Count 1 second.
Yeah, 1 a second, yeah.
It's a billion seconds.
Billion seconds, you know how long that is?
A lot of seconds.
It's a lot of seconds. It takes you 11 days to count to a million. If you count one number every second. You know how long it takes you to count to a billion? 32 years. If you guys were counting since you were born, did nothing else, you guys wouldn't reach a billion.
That'd be so satisfying though.
Like as a life goal. Like I've counted to a billion. You put that on a resume. Yeah, I've counted
What if you don't?
to a billion.
Yeah.
It's one of my life. Something I'm going to do in my life right now. Okay, yeah. We don't want to do that in class though. So this is how you count all the phone numbers. There are a billion possible phone numbers in this scenario. Okay, you have 3 shirts, 4 pants, 2 jackets, and 4 ties. You have an office dress code. So we have 3 shirts, 4 pants, 2 jackets, 4 ties. There is a dress code you must obey. Shirt, pants, jacket, or shirt, pants, and tie, pants, tie, and jacket. We don't care if you wear shoes. But show up to the office, you better be dressed in a shirt, a pants, and a jacket, or a shirt, a pants, and a tie, or shirt, pants, tie, and jacket. How many possible work outfits could you make? Ideas?
We use the multiplication rule.
Sure.
So you have 3, the first one, you have 3 shirts times 4 pants times 2 jackets.
So shirts, pants, jackets. We have 3 possible shirts, we can pick 4 possible pants, we can pick 2 possible jackets we can pick. So how many outfits here? Multiplication rule, 3 times 4 is 12, times 2 are 24 outfits. Is that the answer? Well, no. Or you can create another kind of outfit. Shirt, pants, tie. 3, 4, and we have 4 ties. So that's 3 times 4 times 4. It's 12 times 4, that's 48 outfits here. Or I could go with shirt, pants, tie, and jacket. Because I'm trying to get a promotion. I'm trying to be an overachiever. Show the boss I take this seriously. We would have 3, 4, 4, and 2 times 4 is 12, times 4 is 48, times 2, 96 outfits. So how many work outfits can we make? You add these. So total number of outfits is going to be 24 plus 48 plus 96. That's going to be
168.
what?
168.
168. Now, you don't want to try on a bunch of different outfits and count them each, but you have 168 possibilities. By the way, this illustrates a principle that we're going to be using to count an exclusive OR. This means no overlap, right? No 2 suits in the 3 categories are going to be the same. To count an exclusive OR, we add. You can translate the word OR to add in the case of an exclusive OR, not inclusive OR. For the case of an inclusive OR should be interpreted as the inclusion-exclusion principle that we mentioned last class, or the class before that. So that's going to be a general principle. Now, if you want to count this or that could happen, chances are you're going to have some sort of addition in there. If there are any overlaps, you'd have to subtract the overlaps. But there are no overlaps here, so that sum is just going to be the answer. Okay. 6, consider all 3-digit numbers. It could be 000 all the way up to 999. Okay, so we're looking at all the possible numbers that are 3 digits long. How many of those will have exactly 1 digit is greater than 5? Now things start to get interesting.
4 raised to the 999?
4 raised to the 999?
Yeah.
I can't do that.
That's more than the atoms in the universe. Like that's a lot of numbers right there.
Do you find the total number of possibilities and subtract the ones you don't?
Or you can set up 3 scenarios where each place.
Yeah, you need to set up, yeah. and then it's
Okay, so
one
yeah,
is
so let's do a
four,
digit.
the rest are nine.
So there's 4 possibilities in the first that take can be greater than 9.
Well, how are you setting up the possibilities? So you're visualizing 3 situations. What is the situation you're visualizing?
So the first one is where the first place at is the one that's greater than.
First place is greater than 5.
So there's 4 options.
So there's 4 options at least in that first place.
So you could choose a 6, a 7, an 8, or a 9. So there are 4 choices here. And we want exactly 1 digit greater than 5, right? Which means I need the others to be less than 5. So what can I put here?
Oh, yeah.
What about equal to 5? Is that
Exactly 1 greater than 5. So we
Five
want
is included.
less than or equal to 5.
So 5, 4, 3, 2, 1.
0, 1, 2, 3, 4, 5. So there are 6 choices here. And there are 6 choices there. So for this first scenario, there is 4 times 6 times 6 choices.
And it's going to be the same.
And you can kind of see that the same thing, you can actually multiply that by 3 to know the answer, but you can just write this out. So let's say the second place is greater than 5. Well, that means there are 4 possibilities here, but 6 in the other 2. So that would give us 6 or 6. And let's say the third place, greater than 5. So that means the 4 choices here, but 6 here and here. That's 6, 6, 4. We're gonna add them together. How many numbers is that? So 4 times 6 times 6 times 3. 400? 32. You guys counted all those numbers so fast. So out of 10,000 possibilities, you guys came up with exactly the 432 I was looking for. Like that. Now you guys are getting it. Okay, so think about the rest. We'll finish up next time. So at this point, we haven't really used any permutations or combinations directly. I think the others actually will be used. So I'll see you guys tomorrow.